For chapter 14, we're going to be talking about regression analysis. Now, I'm going to be focused more on you looking at the output from Megastat. So a lot of the equations that they have you doing manually within the book won't really apply. So I would suggest you look at the screencasts and slides as sort of a guide to see what you should focus on when you're reading the chapter. So regression analysis is all about making predictions. Maybe wanting to know if price is going to predict sales, or social media use predicting performance, or GPA predicting starting salary. So it's all about making predictions. So it's a really powerful tool. Here's some of the questions I want you to be able to answer. So it's kind of an overview slide of what we'll be covering. What's the strength and direction of the relationship between the independent variable and dependent variable? So at this point, we'll just talk about two variables. We'll look at that visually with a scatter plot, and then look at the correlation coefficient, which is basically a numerical way of showing the strength and direction of the relationship. We'll look at the regression model. How can we make a prediction about, say, salary given a certain age? How do you interpret the slope of the regression equation? Is the intercept meaningful in that regression equation? And then we can also determine what percent variation in y is explained by x, y being our dependent variable and x being our independent variable. But we'll talk about that later, and whether the model is significant. I like to end with that because it sort of allows me to summarize what we get with the final output for regression analysis. Okay, so let's first talk about the strength and direction of the relationship between two variables. That's a great starting point, because if you don't see any relationship whatsoever, there's not really a need to continue with the regression model. Okay, so first step, we create a scatter plot to see the association or pattern. Remember back when we were talking about ways to describe data visually, scatter plot was one of them, and it was the only one that we talked about that shows the association between two variables. So let's say we have age predicting salary, two variables that we would expect to be somewhat correlated. Okay, so I get some data on age and salary, each person's age along with their salary. And I go to Add-ins, Megastat, and here we're going to go to correlation regression. Okay, so you can see it kind of goes through the steps in the right order. Scatterplot looking at the correlation visually, correlation to get the number for the correlation between the two variables, and then the overall regression analysis. Okay, so if I go to correlation regression, scatter plot, and then I select the horizontal axis first. So basically the horizontal axis is going to be the independent variable, the thing that you're expecting to be doing the predicting, the thing that would come first. Basically in this case, we would expect age to predict salary. We wouldn't expect salary to predict age. In fact, nothing would really predict age because you just age a year every year. So the dependent variable is salary. We're expecting that salary is dependent on age. Okay. So you select the column of data for age and put that in the horizontal axis, and then dependent variable salary. So you select the data for that. And you can put a chart title as well. So I typically put something like age versus salary. Okay, just a note about the independent and dependent variable. The x-axis is always the independent variable. So think of that as the thing doing the predicting or causing the other variable to occur. And the y-axis is always the vertical. So the dependent axis, it's dependent on the x. It's dependent on the cause, or the horizontal axis, the effect. Okay, so horizontal is the independent variable, the one that does the predicting, and the x-axis, and the vertical is the dependent variable, the one that's being predicted, the y-axis. Okay, so I'm going to choose age as my horizontal axis. That's the x that I expect to be doing the predicting, so it's the independent variable. Whereas the salary is the dependent variable, so that's going to be the vertical axis or y-axis. So I would select that column for vertical axis. And then as you can see, I put the chart title in there, age versus salary. And you can leave the defaults here as well. Those are going to be helpful just as is. Okay, here's the end result. You basically see that it is a positive upward sloping line and the dots are fairly close together. So we're basically kind of seeing a strong positive correlation in my scatter plot. You also see that it's giving you an equation and an r squared. That'll be important later on. Okay, scatter plot visually shows me strength and direction. So pretty strong positive correlation. And notice the regression model is there. We'll talk about that in a minute. And r squared, we'll talk about that later. Okay, but it's just a visual. So after creating a picture of the data, we want to then summarize using numbers and see if those numbers are actually significant. You know, right now I'm just guessing there's a positive, strong correlation just based on the scatter plot. So our objective is to quantify the relationship between the two variables with the correlation coefficient. Okay, and relationships can take on many different shapes, such as linear, quadratic, or exponential, but we're actually going to focus on linear because it's very common, it's simple to see, and you may also remember that it's pretty simple to model. The equation of a line y equals mx plus b, our regression equation is basically going to follow that format. So we're going to stick with linear relationships right now between one independent variable and one dependent variable. Okay, this is called the correlation coefficient. It's the strength and direction of linear relationship between two variables. So it's basically the number associated with what the scatter plot was showing you. It can take on values from -1 to 1. So basically a strong correlation is going to be an R close to 1 or close to -1. So basically a -0.8 would be a strong negative correlation. So basically they move in the opposite direction. You know, maybe age and mobility. As you get older, your mobility goes down. A strong positive correlation might be something like age and salary. As you get older, you should probably make more. Okay, let's look at some other examples. If the dots are scattered all over the place, that's basically showing a zero correlation. -3, you can kind of see the dots sort of tend downward for a negative correlation, but they're pretty weak, spread apart, so it's just 0.3. It's not very close to -1. Correlation of 0.5, kind of in between. -0.7, you see pretty tight in terms of the dots being close to each other and negative sloping. Okay, and here's a 0.9. Very high positive correlation is going to show basically upward direction. And the scatter plot you get from Megastat actually gives the trend line on there, so that's helpful. Strong negative correlation. Two things opposite would be -0.99 for the correlation coefficient. So let's look at some specific examples. Wife's age, husband's age, we saw these when we were talking about scatter plot back in the earlier chapter. You can see positive, strong correlation. The dots are very close together, they're upward sloping, and we would expect that. You know, husband's age is going to be correlated with wife's age because people tend to get married around the same age. Whereas for golfers, the grip strength, arm strength, still an upward sloping positive correlation, but not quite as strong as the ages would be. Okay, so for the next step, we want to actually get that number. We want to get that R. We saw the scatter plot, the visual of it, but we want the numerical version of it. So I go to correlation regression again, and the second thing is correlation matrix. You basically select the two columns of data, including labels, and it'll give you this correlation matrix. You don't have to worry about the critical values. It's basically going to highlight a significant correlation depending on confidence level. The confidence level is defaulted to 95. So if it's highlighted, you have a significant correlation, which we would expect here. We would expect age and salary to have a significant, and it's positive, significant positive correlation. As people get older, they should make more money. And it goes the same for someone at a younger age would make less money. Okay, so they move in the same direction. Someone at a lower age is going to make less money. Okay, so just saying positive correlation doesn't mean, you know, higher salary, higher age. It also means lower age, lower salary. They move in the same direction. Okay, and just a note, correlation is not causation. It's very different. Age does not cause salary. We just know that they move together. Typically, people at higher ages are going to have higher salaries. People at lower ages have lower salaries. Another example that you may have heard before is crime rate and ice cream sales are very highly correlated, but obviously there's no causation there. Crime rate's not causing ice cream sales to go up. Ice cream sales aren't causing crime rate to go up. What's actually going on is high temperatures in the summer lead to both high crime rates and higher ice cream sales. Okay, and here's a picture of that, scatter plot of that. You can see fairly strong upward sloping positive correlation, but not causation. Okay, just a few notes about correlation. It's not appropriate for categorical variables, so think about gender. You're not going to put male-female on a scatter plot, right? That would be kind of difficult to do. R has no units. It's basically just either it's close to 1 or close to 0, close to -1 or close to 0, and it's either a significant correlation or not. And it's also not resistant. It is affected by outliers. Okay, we can test for the significant correlation. Now you don't have to know all the details of this because Megastat actually highlights whether the correlation is significant or not. But it's useful to know that rho is the symbol for the sample or for the population correlation, and you're actually doing a hypothesis test like we saw in chapter 9 and 10. The null is that correlation is not different from 0, and what you're trying to test is that it is significantly different from 0. So basically when that correlation is highlighted, it's significant and it's significantly different from 0. And here's what goes into that. You've got a T for the test statistic, sample size and correlation are going to be part of that. But again, and the degrees of freedom, but again, Megastat's going to calculate this for you. Okay, so is there a significant correlation between age and salary? We're expecting positive correlation. As age goes up, salary goes up. And yes, we saw that the 0.8 was highlighted, so there is a significant correlation. So let's look at another example, a similar question. Is the correlation between brain size and IQ significant? I might expect a positive relationship. You know, oftentimes people say when they see a baby with a large head, oh, they're just going to be very smart, kind of like my son. So let's look at some data and see. You know, we can run the correlation analysis and see if it's a highlighted correlation, see if it's significant. Okay, so first step is get the data, decide which would be the independent and which would be the dependent. So in this case, I would expect brain size to predict IQ, not the other way around. You know, you're born with a certain brain size, and that might predict IQ. We wouldn't expect IQ to predict brain size. Okay, so horizontal axis is going to be brain size, the independent variable, the one doing the predicting. And then the vertical is IQ. That'll be the dependent variable, the one being predicted, the one dependent on brain size. Okay, so I had this data from 10 babies. The brain size index was recorded in pixels and IQ later on in life. So the brain size would be in the horizontal axis and the IQ in the vertical axis. And again, I can label that brain size versus IQ is typically what I do for scatter plot. Okay, here's the end result. So it looks positive, slightly positive, but not very strong. The dots are pretty scattered. So let's check the actual correlation coefficient, the R. Again, that's the next step. So we did the scatter plot. Next step is the correlation matrix. And I can just select both columns of data, including the labels, as you see here. That's the input range. Both columns, including labels, together. Hit OK. And you have a correlation of 0.359. Notice it's pretty low, you know, it's close to 0 and it's also not highlighted, so it's not a significant correlation. Part of that could be the small sample size, but based on this sample of 10, we do not have a correlation between brain size and IQ. Okay, so let's look at some other examples. What might you expect to be the correlation for time spent practicing yoga and anxiety level? You would expect the more time spent practicing yoga, anxiety levels should go down. So that, since that's an opposite relationship, that would be a negative correlation, but probably a significant correlation, so -0.8. What about correlation for caffeine intake and anxiety? You would expect the more caffeine, the higher anxiety. Less caffeine, less anxiety. So they move same direction, so 0.8 would be the most likely there. And most likely correlation for hours spent studying and GPA. Again, you'd expect them to move together. The more you spend time studying, the higher the GPA. So that would be A, 0.8. Positive 0.8 correlation. And hair length and salary, obviously zero correlation there. Okay, next up is going to be the regression model, running the regression analysis.